This video is an introduction to the lab number 4 for 47 on operational amplifiers. Measure some of the basic non-ideal characteristics such as offset voltage, input bias current offset, and bandwidth. Offset voltage. In an ideal amplifier, if the inputs are connected together, like in this case, the expected output is 0. In reality, it turns out that it's not. In the plot that we have on the left, it's clear that for the output to be 0, right? This is the output. For the output to be 0, the input needs to be minus 5 millivolts. So we say there is a minus 5 millivolts offset in this amplifier. Now the representation is with the circuit that we have on the center, right? For this, you have 5 millivolts here, right? Right now it's 5 millivolts. So for the output to be 0, we need to add a voltage between 1 and 2 that basically counters the minus 5 millivolts, right? In this case, it would be plus 5 millivolts that cancels. So now this is our tool to analyze circuits. Like for example, here you have an inverting configuration, right? Where the output voltage, if we use superposition, of course, is minus R2 over R1 with respect to the input signal, but plus the offset voltage. And in this case would be a non-inverting configuration, right? If we set VI to 0, so that would be multiplied by 1 plus R2 over R1, right? Actually this is not the output, right? This is the offset voltage. Okay, so that would be the complete analysis of a circuit that includes the offset voltage. Input bias current. So especially on BJT technology, the input to the operational amplifiers are typically transistors, right, where the input is connected to the base. And for the BJT to operate, we need at least a little bit of current on the base, right, current on the base. And we call that the input bias current to BJT amplifiers. Now this current is expected to match, right? The IB in the terminal N is supposed to be equal to the terminal P if the input pair is fully symmetric, but in reality there is small differences. So the difference between the two, right, IB P minus IB N, the difference between the bias current, is what we call the input bias offset, and we intend to measure that amount in the current lab. Okay, we have here a quick explanation of where these currents come from. We have the two inputs, and therefore we are going to have some current, right, going from left to right. That's our input bias. Chances are the transistor 1 doesn't match with the transistor 2, and therefore the currents are going to be a little bit different. And the other thing is that the left side of the circuit is supposed to match with the right, Q1, Q2. These transistors are supposed to match. The current on one side is supposed to match with the other, but in reality it doesn't. And in addition to that, this circuitry might introduce an offset such that when you tie these two inputs together, the output not necessarily is going to be 0. Now, important to notice that if you do this experiment in the lab, every setup is going to produce different results. We have here the offset distribution. It's not a single number for all parts. You have, in this particular case, they took 100 parts and they measure the offset. And yes, it is kind of a Gaussian distribution with a center, right? Notice that in this case it's not centered around 0. In these days, designers are supposed to design for the distribution to be centered around 0. Right? In this case, you have a offset maybe around 0.2 volts that we call the systematic offset on the circuit. There is random offset given by the distribution, right? And you can do the standard deviation to measure how spread is the offset. And the systematic offset is basically when the average doesn't match 0. Now, another important parameter is the gain bandwidth. What we have is a frequency response of the, this is the corresponds to OPA 322 operational amplifier. And we have a dominant pole, right? This is our dominant pole. All operational amplifiers have a dominant pole. The DC gain, in this case, is 130 dBs, which corresponds roughly to about 3 million, right? So we have 3 million right there. Now, important to remember that for practical use is that all the points past the dominant pole follows some interesting effect in which the gain multiplied by the one will remain constant past the dominant pole. So, for example, this one, you have this is about 20 megahertz. So this is 20 megahertz when the gain is 0 dBs. In other words, when you have unity gain. Now, if we actually look at all the other points, like for example this one, now this is 2 megahertz, but the gain is 20 dBs, which in linear scale is 10. So 10 multiplied by 2 megahertz give us exactly the same number as before. And we can continue all numbers, right? This one is based at 2 kilohertz. So 2 kilohertz multiply kilohertz multiply by the gain, which is 80 dBs, in other words 10 to the fourth, give us the same number we have in the unity gain. Now, important to notice is that we can find actually the dominant pole location, because if we follow the same logic right at the intersection with 130 dBs, which is about 3 million, we are supposed to have the same product. So we take the 20 million, sorry, 20 megahertz divided by the gain right there, which is about 3 million, and that gives us a pole about 15 hertz. So we can say that in this particular case, the pole is located at 15 hertz. Okay, a little bit of background. This is already in the lab manual. The input offset voltage is basically defined by this amount, and it's actually not very difficult to find, right? If we take that the offset voltage is in series with the positive input, you have that the gain has to be basically the ratio of the resistor, right? R2 to R1 plus 1, so 1 plus R2 over R1. So what we have is then a ratio of R1 plus R2 divided by R1, and this is my output voltage with respect to the offset. So you solve for the offset. Of course, you encounter this equation that we have here. Now, we have, at the same time that we have input offset voltage, we are going to have also current going into the operational amplifiers that have BAT inputs. But notice that this is 100 kilo ohms. So this voltage over here is going to be the bias current multiplied by this resistor, 0.1 kilo ohms. It's going to be a very small number compared with the offset voltage. So we can say that V out 1 contains only the offset voltage. Now on the bottom side we have a much bigger resistors, this time it's 10 kilo ohms. So the voltage over here is going to be produced by the input bias current multiplied by this resistor, right, R1, and then the bottom resistor, this one, is going to be the bias of the second transistor times R0. Okay, they are supposed to be equal, so ideally the two input sides are equal with respect to the input bias current, but if there is an offset, that is no longer that's no longer true. And this expression that we have here is intended to represent that. And you can derive that equation just following the same circuit analysis techniques we have been using. DC gain. So in the frequency response plot, you have of course the dominant pole, but we have the gain when the frequency is very low, right? We call that the DC gain. Right here for the 741 is about 200,000 according to the manufacturer. So what we want to do is to measure that. The setup in the right hand side is going to help us accomplish that. Well, in this particular case, you have a inverting configuration with the device under test. We can expect the output to be equal to the minus the voltage, sorry, the ratio of the resistor, right? In this case, is going to be about 480, 470 negative. Now, if the voltage on this node, if the amplifier was ideal with a gain of infinity, we were expecting that to be 0, right? Have 0 here. We expect that to be 0 for an ideal one. For the real one, it's going to depend on the gain of the amplifier. There will be a little bit of voltage there, different than 0 due to the finite gain. Now, what we have on the bottom is another amplifier based on FET technology. So this one is not supposed to have offset, right, or input bias current. and is set to a gain of basically 100 to amplify the gain on the negative node of the device under test. This is going to help us find the DC gain, and we have an equation here to determine that. Low frequency gain. In the previous slide, we have basically the frequency response plot in which you have the DC gain, right, at the very low frequencies, DC, right? And then we have the dominant pole, but what we're interested in this particular part of the experiment is to measure the low frequency gain, some point in the minus 20 dB decay on gain, right? And this is going to help us also eliminate the offset voltage, because if it's IC, an AC signal, it doesn't matter if it's shifted a little bit up or down with respect to the 0 volts. So what we are going to do is to apply a little sinusoidal under 1 kilohertz. So if you apply a signal of 1 kilohertz, we expect the gain to be the unity gain bandwidth right here for the 741 would be 1 megahertz divided by 1K, that's 1000. So the sinusoidal that we expect to see in this particular node is going to be the output sinusoidal, right? You actually make it, let's say for the sake of this discussion, 1 volt. This is going to be 1 millivolt right there. And then we use the second stage to amplify that. This stage has higher bandwidth and has no offset, so we can use that to amplify the 1 milli, actually not 1 milliamp, right, 1 millivolt, and have an estimate of the gain of the device under test. And we have here an equation that is going to help us find that gain at a specific frequency, like 1 kilohertz in this particular example. Now, as a way to correlate the results from the previous slide and make sure that it's actually a single pole that defines the frequency response, we're going to find the high frequency gain over 100 kilohertz. So let's say you do it at a over 10 kilohertz. So let's do it at 100 kilohertz. If we do this, and this is a 741 in which the unity gain bandwidth is 1 megahertz, we expect a gain of 10, right? It's only a gain of 10. So what we can expect here is the output sinusoidal, V out 2, divided by 10, and could be small, well, no longer that small, but we have the help of the bottom amplifier with the one difference with respect to the previous slide. We have it configured as a unity gain. Why is that? Well, if you put the oscilloscope probe here, you might be disturbing the experiment. Having the buffer on the bottom gives you an output which is equal in magnitude, but we are not touching the node under test. And the idea is then to confirm 2 points, right? In the frequency response plot, we already did the DC point, and then now we're getting 2 points at 2 different frequencies. Now, gain bandwidth product. So that can be obtained from the 2 previous experiments, right? Because we have gain and we have bandwidth, which is the frequency that you use for your experiment. In fact, you can actually attempt to do the 3D point intersection by increasing the frequency on the input until the output becomes basically equal to the input, and by input and output I mean the input and output of the amplifier, right? Not the closed loop gain, but the open loop gain. Still, we have here an equation that we can use and have an indirect measurement with any of the 2 previous slides, or we can attempt to measure it directly, right, by finding the point in which the gain is 1, right? You remember this is the open loop gain, the gain from input of the amplifier to the output of the amplifier. For the pre-lab, the first step is to find in the datasheet of the 741 and the LF356 the typical parameters. So you can do a web search, and this is a TI part, LM for 741. If you don't find all of them, there is a part that is quite similar, the mu A 741, made by National Semiconductor 741, and currently owned by TI. They own both parts, but the mu A 741 tends to be a more complete datasheet. And then you have the LF356, and basically this is just an activity to fill the table. Okay, what do we want for the pre-lab? First, derive the equations. I helped you already with the first one. The second one is pretty straightforward, following the same procedure. Step number 3, use a simulator to test our setup. Make sure that we know what to do when we get to the lab. In this case, the recommended signal is 10 millivolts peak to peak at the input, 1 kilohertz. Notice that then the voltage at the negative terminal is going to be really small. That's why we are amplifying that signal by a factor of 1,000, right, with the bottom part of the circuit. Okay, the next one is to derive equation number 5 for the circuit shown in the figure 2b, which I have it in the right hand side. And then we want to simulate this to make sure that we know exactly what to expect when we do the experiments. Lab procedure. Basically, we just have to follow the steps. It's very straightforward. You remember the objective of this lab is to find DC gain, unity gain bandwidth, confirm the slope of the gain frequency response, then find the offset voltage, input bias offset, and well, in this case we are not measuring directly the input bias current, and that's basically it for this lab. Finally, we have some questions for discussion. Is the device's experimental data actually matching the theoretical one, or at least the manufacturer's datasheet? Now we are asking the questions about the measurement setup. In this case, does the load actually matter when we affect the gain? That kind of have to back up and redo the experiment, right, to with and without the load. Does the gain bandwidth product depend on the frequency of the input? That's for you to answer once you complete the experiments. Then we have the offset voltage and the DC gain. Are they approximate or exact? I think the answer will be very simple to answer once you have the measurement. And how far is the measured data from the manufacturing datasheet? Just remember, the datasheet often shows us only the average or the typical, not necessarily what you have in your individual part. And I recommend comparing your results with other students, because they are not going to match totally. Okay, thank you.